So thank you, yes, the Institute of Advanced Studies for the invitation to present some aspect, some state of the art, in fact, of what we are doing in the area of organofluorine chemistry at the frontier between fluorine chemistry and biology and life science. The title of the talk is Fluorine in Life Science, the surprise guest. So why fluorine? Maybe we should. Okay, that's it. Okay, so my colleague Surya Prakash from the University of Southern California is used to say that fluorine is a small atom with a big ego. You will understand. Fluorine is the smallest halogen, and it has very strong electron withdrawing effect. So it's a very special element. Why we can consider it as a surprise guest in life science? So fluorine is quite abundant in the universe, and also in the Earth crust. It's the 13th most common element. Fluorine and bromine and iodine being less abundant, but intriguingly, it's virtually absent from the biosphere. There is almost no fluorine, just a few fluorinated compounds, organic compounds, in the biosphere. And it's an enigma compared to the more than 5,000 known microproducts incorporating halogen, such as chlorine, bromine, iodine. Why so little fluorinated compound, organofluorinated compound? But in fact, the natural mineral source of fluorine, which is calcium fluoride, is practically insoluble in water. So it's difficult for microorganisms to metabolize this fluorine. And also, even if it's slightly soluble in water, the hydration energy of fluoride is very important. So it's difficult to metabolize and to create nucleophilic weak and to create carbon-fluorine bond, which is in fact the kind of molecules we are looking for. So fluorinated compounds, organic compounds, have to be synthesized by chemists. And that's our job. First of all, one slide, 1 minute organic chemistry course. Like that, everybody will understand what I will speak about, and I will try to be understandable. So you know that molecules are assembly of atoms linked together by chemical bond. So in organic chemistry, we generally represent molecules like that. We just represent the skeleton of the molecule. And this kind of bond here means that fluorine is forward, and this kind of bond here means that hydrogen is bound forward. So that's molecule here is represented like that. Because I will show you some molecules. It's interesting to give this precision, this key. The art of organic synthesis, how do we proceed? Because that's our main skills here in the lab. How do we proceed to synthesize this kind of molecules? So, for example, I take the example of trifluoromethylalanine, which is a molecule that we are using a lot. So we start from a commercially available or naturally available starting material. And it's the game of breaking bonds and creating new bonds and to synthesize intermediates. So for example, by creating new bonds here and by cutting this bond here, we obtain this intermediate. Then we break this bond, and we create a new bond between the cyano group and this carbon, and we obtain this intermediate. We cut this bond, and we obtain our target molecule. I will not go more deeply in synthesis, but it's the background work, and it's really a huge work to synthesize even the simple molecule. And also, what is important is to control the chirality here, because we have three-dimensional object, and this architecture should be carefully organized in the space. So there are some few purity natural products which has been isolated so far. For example, this one, and David O'Hagan discovered the formation of the mechanism of formation of this compound. And he isolated an enzyme, fluorinate, which is able to incorporate the fluorine atom in this position to this adenosine methionine to give this compound and to create this carbon fluorine. Other examples are known, have been isolated, but it's just a few. It's something like 15 compounds, fluorinated natural product, and only monofluoro compound. So it's not useful. There are rare compounds useful for the synthesis. So that means that we have to synthesize fluorinated compound from the only natural product we have, which is fluorspar, which is calcium chloride. So everything will be constructed around HF, which is hydrogen fluoride, which is a gas. So starting from calcium fluoride by acidic attack, we obtained HF. As you can see here, the world repartition of fluorine producer in the world. The most part of the most important part of fluorine compound produced are produced in China, and also HF is produced in Mexico, some in Mongolia, Russia, and for the EU it's only 4%. So we are very dependent from China in the geopolitical point of view, and they are doing a great effort in developing the chemistry of fluorine. Yes.
This geopolitical graph of fluorine production, is it something similar for most of chemistry around the world, that China is the big producer, or is there something specific to fluorine?
It's specific to fluorine and also rare earth.
Yes.
And the rare metals, and so for nitrogen, for example, you have nitrogen everywhere. So everybody is able to produce ammonia, for example. But for fluorine compound, no. Yes, very important. And I will show you in life science and in the pharmaceutical, pharmaceuticals are really increasing in importance. So that's why from a geopolitical point of view, it's very important to know now that fluorine chemistry, basic compounds are coming from from China. No.
Is it very mostly found in Asia?
Where?
Before in countries before is that mostly found in Asia? In China or
It's in Asia, mainly, and also in Mexico.
is that okay?
Yes, for the production. But in fact, this raw HF is produced in situ generally, and it's exported.
Because, for example, lithium, most of it is in America, no?
Mhm.
But if you make whatever private sector is very we so lot of fluorine that we may think about our relation with China to end.
I will show you. Yes, I will give you the answer here, which is illustrated, which is the illustration of the organic fluorine application, organic fluorinated compound applications. So you have crop protection. You have the polymer materials, for example, Nafion, Teflon, all these stuff. Refrigerant fluid, almost all refrigerant fluids you have in your car, insulation and things like that, are fluorinated. Storage of energy, very important. For example, fuel cell need fluorinated compound, membrane, fluorinated membrane, Nafion, things like that. Nuclear energy, because for the enrichment of uranium, you need fluorine, because the enrichment is done by centrifugation. So you need to have a gas and exactly chloride of the uranium to the gas. Electronic devices, LCD screen, for example, liquid crystals. And also, I will focus today on medicinal chemistry and chemical biology, diagnostic. So there is really a lot of application. So if I focus on the most important in terms, not maybe in quantity, but in money it generates, let's see now the importance of fluoropharmaceuticals. Some milestone dates. So in fact, it's quite new. The first molecule here on the market has been launched on the market 70 years ago, something like that. So after Second World War, which is this one, the fluorocorticoid. Then in the 90s, there was some kind of a revolution with the fluoroquinolones, which are potent antibacterial agents. And what was very interesting that the mechanism of action of these molecules is completely different than the other the previously reported antibiotics such as penicillin and cephalosporin. And it's important to always find new drugs involving new action of mechanism in order to bypass resistance. And then the winner whole category for medicinal chemistry and the pharmacy is Lipitor, which was launched on the market in 1997. And this one is considered today as the most profitable blockbuster drug of all time, with a sale exceeding $120 billion during its whole patent life. Last 30 years, here. You have we can consider that fluorine-containing molecules are comprised between 20 to 30% of all drugs in the pharmaceutical market, and it's constantly increasing. So on this graph, you can find fluorinated fluoropharmaceuticals in the green, and in the light gray small molecules, and here all the new approved molecular drugs per year. For the last 5 years here, as you can see, it's increasing, and it's now it attains 2018, 2019, 50%, 43%. So it's really a huge increase. Classification of the therapeutic use of these compounds is very wide, in fact, from skin disease, antimicrobial molecules, anti-tumoral, gastrointestinal and metabolism action, antipsychotic agent, circulatory system, antiviral, non-steroidal anti-inflammatory drugs, and so on. So a lot of applications. Some example of the most important blockbuster molecules launched in the market in this area. About 25% of the current blockbuster drug contain fluorine. We call blockbuster drug sold at more than $1 billion or greater per year. They generate a big money. So, from a chemical point of view, you can see all the application from the biological point of view. Here, for example, this one, mefloquine, maybe you know, Lariam, for malaria, anti-HIV compounds such as efavirenz, antipitabine, and this one. These two compounds are very important. Sofosbuvir and glecaprevir to treat hepatitis. So you can see that this one, just in 2019, it gave $1.9 billion from a chemical point of view, you can see that we have the chiral compound, CF3 compound, monofluoro compound, CF3 group or fluorinated group on aromatic ring, in alpha position of double bond here. We have chiral CF3 compound, chiral monofluoro compound, and so on. So there is a big diversity, chemical diversity in this compound. And a special mention for this kind of compound here with fluorine 18. I will explain later what is this fluorine 18, because all these fluorine here are fluorine 19. Fluorine 19, which is the natural isotope, and fluorine 18 here, this one is the radioactive artificial isotope. I will explain the use for the TEP for the diagnosis of cancer. So what is very interesting, in fact, with fluorine is that it's a formidable, wonderful tool for the rational design of pharmaceuticals, because it depends on in what place do we put fluorine, how many fluorine, and the consequences on the molecule you can have to explain its biological activity. So first of all is the hydrophobicity or lipophilicity, which is the affinity for membranes, for example. So for the brain, for a drug to go into the brain, it has to cross the blood-brain barrier, blood-brain barrier, and it has to be hydrophobic. So with fluorine, as you can see here, compared to hydrogen here with 1 fluorine or CF3, 3 fluorine, or OCF3 group or SCF3, we increase hydrophobicity. The winner is SCF3. It's the most hydrophobic group as well. Until now, and some example with the Prozac, for example, there is a CF3 group in this position. We usually also the OCF3 group here. Another interest in fluorine is the isosteric replacement by fluorinated. For example, the phosphate is a very important group in biochemistry. But very often this bond here is hydrolyzable. So it can be broken very easily. So the idea is to replace this bond by a carbon phosphorus bond, which is more stable, of course, completely stable. But in this case, we lose acidity of the phosphoric acid. If we incorporate 1 or 2 fluorine here, we restore this acidity, which is important for the molecular recognition in enzyme. Another isosteric strategy, we say isosteric, that means same side. It's the replacement, for example, of this amide bond, which is hydrolyzable here, by an alpha CH3 amine here. So you have the same polarity here, and you keep this hydrogen bond donor here. So it mimics, in fact, the this function, but it's not hydrolyzable. So you will have better biological activity. Another example, you remember there were a lot of fluorine on the aromatic ring. When you take a drug, in fact, you take a toxic and it's a xenobiotic. So your organism will try to remove this drug. And for aromatic compound, so aromatic is this kind of compound, the way to detoxify is the oxidation of this aromatic ring into a phenol, and then the phenol here is hydrophilic, so it goes in water, in the urine, and it excreted, and you are detoxified by this way. But the problem is that if it's a drug here, if it's detoxified too early, you don't have the therapeutic effect. So that means that you have to use a huge quantity of certain drug to have the biological effect. So the idea is to replace this carbon hydrogen bond by a carbon fluorine bond or carbon CF3, and in this case there is no oxidation. So as there is no oxidation, we increase what we call the bioavailability, like the plasmatic half-life It's the time where in your blood you lose half of the compound. And if you decrease like that, you can decrease the drug amount administration. So you have better effects, better activity, and of course, less toxicity, because there is always side effect with pharmaceuticals. An example here, it's this molecule, which was developed for cholesterol absorption inhibitors. And the weakness of this molecule was here, oxidation here. And they discovered that if oxidation is here, it's a beneficial effect. So it's positive. Dealkylation here is also positive, but dealkylation here is not positive. So the design using fluorine of this molecule was to fluorinate this position, to incorporate an hydroxide group here, which is an oxidized group, dealkylation here, and then dealkylation here and incorporation of the fluorine in order to avoid the oxidation. And like that, you can obtain rationally a compound which is 400 times more potent than the first generation molecule. Other examples, use of fluorine to stabilize molecules, to hydrolysis. So, for example, this one has an half-time of 10 minutes. If you incorporate one fluorine, half-lifetime is 1 month, and with 2 fluorine, 90 days. So in this case, you have a very good activity as platelet adhesion inhibitor. Another example here, this first generation HIV reverse transcriptase inhibitor, half-lifetime 30 seconds at pH1. pH1 is what you have in your stomach. With just 1 fluorine here, you have the same HIV reverse transcriptase inhibitor, so it's for AIDS, treatment of AIDS, and this one is orally administrable. So it changed everything because for AIDS, which is chronic disease, it's mandatory to take orally available drugs. Another example, so this one is unstable, and this one. I like very much this example. It's the last one, trifluoridine. In this case, it's a very, very specific fluorine process. It's what we call mechanism-based inhibitor or suicide inhibitor. So in fact, here you have a CF3 molecule, trifluoridine, with 3 fluorine. And during the process, the trifluoridine is using 1 fluorine, 2 fluorine, 3 fluorine, and the results, chemical results and biochemical results of all these reactions is to bind definitely this molecule into the active sites of the molecule. And this binding is irreversible. So that means that in your enzyme, your catalytic site, in fact, is occupied by this molecule, which has been irreversibility bound to. So that means that your enzyme is not efficient anymore. So it's completely inhibited. So it's a very important antiviral compound. Okay, so I move to another aspect, which is more connected to chemical biology, is the use of a fluorine NMR. So examples of the literature. So this is an NMR. We have one here, the biosys. And it's the way to analyze the compound. In fact, it's an analytic method. So we put the sample here in a glass tube, and after registration of spectrum in the NMR, the nuclear magnetic resonance operators, we obtain a spectrum like that. And to one spectrum, in fact, correspond one compound, one fluorinated compound. And what is very important is that fluorine is very sensitive. It's as sensitive as a proton. Chemical shifts are very sensitive to the environment. So that means that, for example, if you have in a protein one fluorinated drug, its spectrum will not be the same as if it is outside. So it's very sensitive to probe the biological processes. And moreover, as fluorine is virtually absent from the biosphere, there is no background signal. So that's why it's very sensitive. So first of all, you have to synthesize and to incorporate through your molecule fluorinated compound. So generally for protein, peptides, we incorporate fluorinated amino acids. So the most interesting one are, for example, this one, because there is a lot of fluorine. So we will have a big signal. Some application, for example, so March and his colleagues studied, in fact, the process and the mechanism of antimicrobial action of one peptide, the MS-78. The question for these peptides is to know whether they are on membranes or if they are doing pores, they are organized in the membrane, doing a pore, and for the antimicrobial action. Because here you have the inside of the cell, and here you have the outside. So if you make a pore, water inside the cell will go out and it will kill the bacteria. So what he did, incorporated these amino acids in the peptide. When the peptide is free like that, we have this signal. And when it is bonded in the membrane, you can see a shift of the signal. And that's the proof that we see inside the Another example like that, you can discriminate in a DNA chemistry during the synthesis of DNA. But with this probe, for example, you can monitor the transition from single strain to duplex strain of the DNA. That's a different picture here. It was the same for kinase, which are enzyme doing phosphorylation of amino acids here. So phosphate is here. So here you have the non-fluorinated, the non-phosphorylated peptide. You have the fluorine signal, and when the enzyme incorporate the fluorine, you have a shift here. So like that, you can monitor the phosphorylation and the action of this enzyme. It's possible, so it's quite new, and it's 10 years old methodology, and there is great achievement right now in also magnetic resonance imaging, what we call MRI. And it's really new, but you need a lot of fluorine. So for example, with this perfect probe, It has been encapsulated recently, so it's here on this publication, encapsulated in mice cells. So mice cells also with a lot of fluorine. So really you have a huge amount of fluorine. And then you can inject it to a mouse with a varying tumor. And you can have an image, you can see the concentration of fluorine in the heart at the beginning, so that means that it's circulating, in the liver for detoxification, and after in the tumor.
What are mice?
Mast cells are self-organizing system with here an hydrophilic head, and here a fluorophilic tail, and it can also organize like that with all the fluorinated tail in the middle. So it's a tensioactive, it works like a tensioactive, and all the water-soluble head outside. So it's like a sphere. And it can, and inside here, you can incorporate this highly fluorinated probe here. And of course, it is soluble in the blood because it presents only water-soluble head outside. And it allows the transportation of what is completely insoluble, this part, it can be transported in the blood. Yes?
Why is it accumulated?
It's because of the circulation of the blood.
Okay.
So when you have a tumor, it's more vascularized, and that's why. But they injected really huge amount of. But you will see with F18 fluorine, it's more clear. Okay, but this one is with natural fluorine. So now I skip to this one, which is not natural, which is a radioactive one, which is fluorinated. For medical imaging, positron emission tomography, which is called PET. So this one is very, very interesting because it's metabolic and molecular and functional imaging. So what you see, in fact, is the biological object you want to see. And it's a non-invasive medical imaging. So the concept is the following. This fluorinating is radioactive and it's emitting the beta plus particles. And these particles are antimatter. When antimatter meets the matter, for example, an electron, there is an annihilation and it provides the emission of two gamma rays in a specific orientation of the space. And with a camera like that, you can reconstruct the image of the body with the localizing the places where there is fluorine 18 has been accumulated. So it's not natural. So you have to do it. And to do it, you need a cyclotron. So you do it in each lab, which it's really a huge operators. But it's commonly used in hospitals. So there are companies producing this fluorine 18. And also, we can prepare fluorinating nucleophilic reagents or fluorine F2, which are electrophilic for chemistry. So I present some application of the glucose, for example, FDG here. We incorporate the fluorine in this position here. And as you can see here on this image, that there is accumulation so in the bladder, so it's normal, it's not a problem. It's because in the urine there is a lot of glucose. Here in the brain, so we need a lot of sugar, also a lot of glucose in our brain. But what is not normal is to have so many fluorinated glucose in this position. And that's generally the marker for cancer, because cancer cells develop very, very quickly and they need a lot of glucose. And also you can see there is a little bit here in the kidney, so it's normal. It's because of the clearance. So this is the principle of the PET imaging. So for example, here you have fluorine here in the kidney, it's normal. In the heart also, because it's second, but here it's not normal. And for example, here surgery could be an indication. In this case here, with all the metastases, it will be a chemotherapy. Surgery is not the recommendation. So that's it. An application in neurology also with this marker DOPA. So the lack of DOPA is a neurotransmitter, and if you don't produce enough DOPA, that's the indicator for Parkinson's disease. So here you can see when healthy control here. So there are DOPA here. Early Parkinson, you have less DOPA, and also latent Parkinson. So it's very interesting, this method, because here sometimes this tumor you can't see by radiography because it's very, very small. But what you see is the physiological function, and you can see that there is more glucose in this area, but by other methods we wouldn't see it. And what is interesting also on this method, which is non-invasive, is that you can follow the treatment. So it's not only for diagnostic, but also for therapeutic, to see if the anti-cancer drug is working or not. If after a few months it disappears, it's okay. If it's still there, that means that we have to change the chemotherapy. Okay, so now maybe if I have some more time. 10 minutes, I will accelerate what we are doing in this area in the group in Cergy. So we are focused on peptides because these compounds are really increasing in the pharmaceutical market, as you can see here. For example, 52 peptides were approved since 2000, so it's really increasing. The problem of these peptides as a drug is that they are prone to hydrolysis and oxidation. They are low membrane permeability, short half-life, and fast elimination. And we think that we can circumvent some of these drawbacks by incorporating fluorine. For example, to increase hydrophobicity, to give better affinity to membrane, and also we can use these fluorinated peptides as NMR flow. The challenge is the synthesis of the amino acid in an pure form, by scalable methodologies, and also the peptide coupling to incorporate these amino acids into the peptides. So we did the synthesis of all these peptides. We reported these synthesis in a pure form and on a grand scale in order to be incorporated in peptides. Then we measured the increase of hydrophobicity. So we compared the hydrophobicity of these peptides, incorporating here natural amino acid or biosphere-made fluorinated amino acid. And as you can see here, so it's the increase of hydrophobicity. All these fluorinated incorporating fluorinated amino acids peptides are more hydrophobic than the natural one. So that means that by incorporating STF3 group, for example, or CF3, we are beyond the natural hydrophobicity, because isoleucine, this one, is the most hydrophobic natural amino acid. So it can be interesting to target hydrophobic.
Must increase.
It's almost like an hydrogen, so like an oxygen, for example. So we will increase, of course, the mass, but it's not a problem. What is important generally is the size. And the fluorine is small. So even if you incorporate fluorine, for example, CF3 group here, it's like an isopropyl group. So that means it's even smaller than this group. Because recognition of peptides with protein is mainly done by hydrophobic interaction and also the space. So even if the weight of the fluorinated compound is higher, it doesn't play in the recognition. So in fact, it's not a problem because fluorine is quite small.
More fundamental standpoint, is that due to the repulsion of the vacuum density around the fluorine?
Yes.
With oxygen?
Yes.
And
Yes. Yes.
why is that? Okay, is that more important than the hydrogen bonds? Is hydrogen oxygen?
Yeah, yes, because here with the fluorine, in fact, the method we use is it's an HPLC method. So what we measure is the interaction of the fluorinated peptide with the reverse phase HPLC. So that means it's a hydrophobic interaction. And of course, with the fluorine, you have a lot of electrons outside. So you have a repulsive effect compared to hydrogen. That means that highly fluorinated parts have fluorophobic interaction with the lipophilic phase and also with water. For example, if you have a completely fluorinated compound, it will be completely insoluble in an organic solvent and completely insoluble in water. So it's a third phase, in fact. So in the case of a biological interaction, I would say that hydrophobicity is recursion of water. That's why it's hydrophobic. It's because it repels water. So that's why it would have better interaction with hydrophilic part of the protein because it removes the water. That's the way I see it. So an application we did, so we synthesized this peptide, which is a fluorinated analog of LIF1, PLG, which has an analgesic effect, and with a colleague, Adriana Bocheva, in a collaboration, she observed that our fluorinated compound was more active than the non-fluorinated one here. And we measured also the hydrophobicity indexes of these peptides, and we observed that hydrophobicity, when hydrophobicity increased, the passive diffusion transport through the membrane increased also. So we propose that it's key maybe to understand the better activity and the better analgesic effect of this compound, because it has to go to the brain. In a collaboration also with Sorbonne Université, we worked also on the use of fluorinated peptides to refrain the aggregation of amyloid peptide. So the amyloid peptide, in fact, are formed by beta-hairpin formation, and then it gives fibrils at the end, and these fibrils, in fact, the cause and the manifestation of Alzheimer's disease. And our idea was to use fluorinated peptide in order to inhibit this aggregation, and indeed, we decrease with this fluorinated peptide. Yeah, we decrease from this curve. You can see it. The aggregation of the amyloid beta. With the peptide here, you have this aggregation, and we can see that 10 images. Another collaboration yet with our colleague Anurich in Karlsruhe. She is doing fluorine NMR, solid state fluorine NMR, to decipher the mode of action of antimicrobial peptide. So what we did in an antimicrobial peptide, we incorporated this fluorinated amino acid here at different places of the peptide, and by solid state NMR, she can measure the orientation of the peptide in the membrane. So we prepared here with the PetLab platform this peptide here, incorporating this amino acid, and Anurich in Karlsruhe measure the orientation in the membrane. And indeed, depending on the membrane, we have the incorporation of the peptide in the membrane. So it's an explanation of the antimicrobial effects. And last slide is the recent publication with Julien. We used fluorine NMR as a tool to probe protease degradation of peptides with the pepsin. So pepsin is an enzyme which degrades peptides. So the idea was to incorporate fluorinated amino acid in the peptide, Then the enzyme is hydrolyzing one bond, and then we have two parts here, and just one part is incorporating the fluorine. And like that, for example, we can see here we have the starting material here, and here we have the product. So this one, which has the fluorine, and like that we can monitor the degradation, and we can monitor also the inhibition of this degradation. And for example, with this peptide, after 40% of the peptide are not degraded after 1 day, but for the non-fluorinated one, with alanine here, in 1 hour, you have no more peptide. And also, we could see that the cleavage site was different to what is expected generally for this peptide enzyme. Okay, so as a conclusion, in the introduction, I said that the fluorine is virtually absent from the biosphere. The reason was that the living organism could not metabolize inorganic fluorine. But have you seen, since the 60s, thanks to the development of organofluorine chemistry, fluorinated drug invested the biosphere. And it's a must, an increasing must in the field of pharmacy. 25 to 50% fluorinated drug registered per year. So the question raising is, what living organism is now available to metabolize fluorine? Of course, it's yes. And we should now take care about the environmental issue of the new fact, which is because in fact it's quite new. We have fluorine, organic fluorine in the environment. So to finish, I will thank my colleagues, Grégory Chaud, Evelyne Chelin, Nathalie Mancel, Julien Petrovich, PhD student, Emmanuel Devilliers, Véronique Johan. It's 5 people working on the illustration from the lab that I presented today, Charlène Gadet, Clément Sanchez, Saint-Catholique, some master students, and also the colleagues working with us in collaboration oriented towards life science. Okay, and I thank you.
Thank you.